So welcome to the Advanced Effect Workshop. We're very excited to have you all here for the first set of workshops that Effect is hosting. My name is Max. And just like a quick about me, I'm based in the USA. All good, Mike? Yeah, okay. Based in the USA, I'm from New Jersey. I work my day job as a senior DevOps engineer at SAP. I'm a core contributor to the Effect library. I have been for, I think it's something like 4 years now. And I guess my claim to fame in the Effect community is that I'm the primary author of the Effect CLI library. And a quick fun fact about me is I am actually a licensed pharmacist in the United States as well, in 2 states. So did not start my career in tech, but here we are. Some of the other workshop facilitators that you'll see throughout the day, I think you know these guys from Discord, but Mike and Tim will both be floating through the 2 workshops that we have going on. So if you have any questions that you don't want to, again, like raise your hand for or anything like that, feel free to ask them. And just a few of the goals of like what we're trying to accomplish today. So we talked a lot about how we wanted to structure this workshop as we were developing it. We talked about whether we were going to build an app or we were going to just go over different design patterns. And we ultimately decided that one of the most useful things that we could give you folks, developers, is to explore advanced patterns in Effect by going over reusable design patterns rather than building a full-fledged app together. So most of the exercises that we'll be doing today will focus on basically practicing using some of these advanced design patterns that you'll see if you look at some of the internals within Effect. And hopefully we can all enjoy ourselves while we're working together. I do encourage you guys to like raise your hand, ask questions, interrupt me if you want. I'm not like super strict about any of that, but if you don't feel comfortable doing that, again, there's the Discord channel we'll be monitoring. And yeah, we'll have a lot of coding exercises to work on together. I'm going to try to minimize the amount of time that I'm like blabbing about. Just a little bit about the schedule. So we have 4 sessions of content for you guys today in this workshop. In session 1, we're going to be focusing on patterns for service construction and resource management with Effect. So primarily with the focus of how do we actually integrate Effect with external libraries and how do we wrap external libraries with Effect? Because even though our ecosystem is growing every day, we still don't have libraries that handle everything. And so there are a lot of use cases for integrating with external libraries. And each session that we have today, except for the final session, will have a session project associated with it where we'll spend about a half hour doing kind of like a larger, more complex little project with some of the things that we learned during that session. So in session 1, our project will be to wrap an Express server with Effect. Even though we have an HTTP integration already, still a lot of useful patterns we can learn. In session 2, we're going to be talking about fiber synchronization and coordination. So how do we synchronize different fibers? How do we communicate between different fibers in our Effect app? How can we really utilize these low-level primitives to build cool stuff with Effect? The session project in this session will be to build a rate limiter. You'll see we'll be going with a much more complex implementation than what we actually ended up with in the core Effect library. But I think it'll be useful to kind of explore a lot of the things that we're going to be discussing. In session 3 in the afternoon, so between sessions 1 and 2, we'll have a 15-minute break. Then we'll have an hour and a half between session 2 and 3 for lunch. At 2 o'clock, we'll get back together for session 3, where we'll talk about batching and caching with requests. So we're going to explore some advanced design patterns surrounding request, try to get a little bit of a better understanding about Effect's built-in batching and caching mechanisms. And talk a little bit about caching computations and building custom request resolvers. So we'll finish this session by re-implementing the data loader request resolver from the experimental library, so don't cheat and look at the experimental library while we're doing that project. But again, like a lot of really useful things that we can learn by doing this. And then in session 4, we'll be doing a deep dive into observability and monitoring with Effect. So talking about custom loggers for your Effect application, exploring the metrics API that we provide, how do we trace applications with Effect. And instead of a session project in session 4, we actually have a application that we built that uses patterns that we'll be discussing throughout the day, which will basically give you guys the ability to play with. We'll give you guys an open AI key, and you guys can play with the app, and we'll talk a little bit about integrating with external monitoring tools and whatnot. Again, before we launch into the presentation, I just want to encourage you guys to ask questions if you have them. And yeah, so let's get started. So our first session is focused on integrating with Effect with external APIs. And when I approach the problem of trying to wrap an external API with Effect, there are really like 3 options that you have. The first option is kind of like the one-off approach, where you don't really need like a full-fledged integration. You're just wrapping like a single API call, and so oftentimes just a one-off wrapper for a client method is enough. The second option is like a little bit more flexible, and probably the most common approach that you'll see when we wrap external APIs to provide you with good library integrations, where we have an effect-based wrapper for accessing the underlying client or API itself. And then option 3 is kind of like all in on Effect. We wrap every client method, every API that we need to integrate with. We have like an effect-based wrapper for. And so we can take a look at some of examples of this. We're going to be looking at code examples today as well. If the code is too small, can you guys raise your hand? Too small. Perfect. Thank you. How's that? Better? Okay, cool. So to kind of exemplify what I'm talking about the 3 options that we have, I chose the OpenAI library as kind of our example. So we want to integrate with OpenAI. We want to be able to make requests to the OpenAI API by using their client library, not one that we've made a custom library for. And again, there are several different options that we have. So if we think about like the one-off approach, right? There are a lot of trade-offs that you have to make when using this one-off approach to wrap external clients. Namely, you end up having to pass in a lot more information to your method calls. You end up with a lot of verbosity in your code because again, each one of these methods that you're calling needs to be wrapped. So in this case, we're using the try-promise API from Effect to wrap the OpenAPI chat completions API. But the point here is that oftentimes this integration is only appropriate when you're only calling these APIs once in your Effect application. A much more common and flexible approach that you'll see even us using inside the core libraries is to create an effect-based wrapper for the client. So in this case, we have the OpenAI client itself, and this call method that we're using here basically receives a function that gives us access to the underlying client, as well as an abort signal. And we can return a promise from this function call. And then underneath the hood, we wrap the whole call with try promise. And you can see, like, just by making this simplification, we get a ton more flexibility out of integrating with this external client, right? The final option is the all-in on Effect approach, where there are certain situations where this approach may be appropriate. Usually, the situations where you might want to consider going all in on Effect is when you want to return some custom data type from calling an external API, like if you want to get a streaming response out of it, or if you have some other custom information that you want to return. A good example here is in this completions API that we've built up here, we take in a bunch of options And you can see by looking at the return type that we're actually returning a stream from this call. So we're still utilizing our flexible wrapper for actually calling the external API, but then we handle the internal stream, wrapping it with effect. And so you guys can kind of get an idea of the different approaches that we can potentially use when wrapping these external APIs. But the question still is, we want to integrate with these external APIs. How do we actually go about doing this? What's the approach? What's the decision matrix? How do we actually go about integrating with these clients? Because we get these questions a lot in Discord. Oh, I want to use X library, but I don't really know how to wrap it with effect. Again, there's kind of like 3 major categories that we have here. There are promise-based APIs that we want to integrate with. I'm not going to belabor this point because this is very, I think, base level. But we have the effect.promise API, which allows us to wrap a promise returning an unknown error. And then if you have a more specific error you want to return, we have obviously try promise, which we've seen already, allowing us to take a more specific error and return it from, basically wrap the errors that we're getting from that API. But I think where things maybe get a little bit more hairy or maybe a little bit more complex is when we have to integrate with callback-based APIs. And some questions that you might want to ask yourself: is the callback API a single-shot API? Is it a multi-shot callback? Or are we at some sort of execution boundary where we actually need to run the effect that we're concerned about? So to get a little bit more clarity here, if we have a single-shot callback, some of the more useful APIs that we have in effect are the effect.async combinators that we have. These constructors allow us to wrap asynchronous callbacks with an effect. So here you can see we want to integrate with the node file system read file method. And we're using the effect.async constructor to basically do this integration. Effect.async is one of the only constructors that we have, or in the small category of constructors that we have, where we don't get automatic where we have to manually annotate the types. And it's because we have to use this resume function, so TypeScript can't actually do the inference for us. But effect.async gives us this resume function, which allows us to call an asynchronous API and resume with an effect at some point later on. So within the effect.async constructor, we can call our read file method. And then inside the callback, we can actually use resume to pass an effect back into the effect runtime. So if we get an error, we can fail that effect and resume with that failure. Or if we get a successful response, if the callback is successful, we can resume with the data successfully. And there are, with the most recent, I believe, release of effect, we've consolidated the async APIs for effect down to just 2. We have effect.async, which is useful when you have a single asynchronous callback to import into effect. And then we have effect.async effect, which is useful for when the callback that you're importing also requires an effectful operation. So taking a look back at async, we can call the callback directly here. But if the logic that we need to perform in this asynchronous callback is effectful in and of itself, we can actually use async effect to do that work, allowing us to actually return an effect within that async call. Both of these methods can optionally return a canceller, and that canceller will be run when the fiber that's running that effect.async method is interrupted. So we don't actually show it off here because we have a quick coding exercise to do here, where we want to basically utilize the effect.async family of constructors to import an asynchronous callback into effect. The requirements of this exercise are basically to re-implement effect.sleep using setTimeout. So we want to take the number of milliseconds as an argument and suspend the current fiber for the specified number of milliseconds, and then resume that fiber once that number of milliseconds has elapsed. And if you guys take a look at the workshop code, under the workshop directory, under exercises, in session 1, you'll see our exercises organized in order. So if you guys would crack open exercise 0, you'll see that we've spec'd out this sleep method. So we're going to take about 10 minutes and try to implement effect.sleep ourselves. And if obviously if there's questions, you guys can discuss amongst yourselves. Feel free to ask Mike or I anything. As a bonus point, your implementation should also properly handle, again, if that effect.async call itself is interrupted by using a canceller. So bonus points. We'll show exactly what I mean, but give it a try. All right, so why don't we spend a few minutes discussing this? So if we crack open, there is a solutions directory in here too, so you guys can explore the solutions if you want. I'd encourage you to try the exercise before you actually look at the solution, but that's up to you. You guys can see the code, right? Like I've checked before, but you guys can see. Raise your hand if you can't see. Can't see, okay. Is that better? A little bit? The solutions are also in the repository itself, so if you can't see, I think this is as big as I can make it. But let's spend a few minutes discussing this, and if you can't see, we'll make an adjustment in the break. But so we can implement. This is a much simpler version of effect.sleep, obviously, than we have in the effect library itself. But the concepts are the same, right? So we want to sleep for some number of milliseconds, and in this case, we're using the set timeout API to do that. So set timeout allows us to obviously, have a delay associated with running some program, and by using set timeout, we can resume the execution of that fiber after some amount of time. And in this case, we can just resume with effect.unit because there's really no information that we want to propagate forward. And I know I mentioned before that as bonus points, you guys could explore what a canceller could be used for in effect.async. So in this case, we can utilize the canceller to make sure that the timeout is properly cleared in the event that the fiber is interrupted. I want to make a note here that the canceller should not really be synonymous with cleanup, because the canceller won't be run if there's a failure, right? The failure should be handled by resuming with that failure. This will only be run if the effect in question is actually interrupted. And so the reason why I'm making that distinction is because this kind of, maybe for anybody who's worked with React, might look a little bit similar to the structure that you get with a useEffect call, right? You have some work that you can do, and then you can return something to kind of clean up that useEffect. But in this case, the canceller that we return would only be run if the fiber that's running effect.async is interrupted. And we can kind of show off this behavior a little bit. I'm going to put my mic down and I'll yell. So we can kind of show off this behavior a little bit if we adjust our program. So let's fork our call to sleep into a separate fiber. So now we're going to be running sleep in a separate fiber, and we can simulate interruption, or not simulate, we can actually interrupt by timing out sleep after maybe millis minus, I don't know, 100. So this is always going to time out our call to sleep, right? If we run this is getting very... As you can see, I ran everything this morning. Right now, we won't see anything because we're not doing anything in the case of interruption. But if we add even just a simple console.log here, oops, I'm very sorry for all the pop-ups. I may have to zoom out just a tiny bit. If we add a timeout here, and then we make sure, and we make sure that this, okay. So a few things going on here. We're forking the sleep into a separate fiber. We don't actually need to do this to exemplify what I'm talking about, but it's kind of useful to have this running in a separate fiber. We yield immediately to make sure that at least that fiber starts. And then when we actually run the program, you can see that interruption occurred, obviously, because we timed out. When you use effect.timeout and you actually time out the execution of effect, it interrupts the fiber running that effect. And in this case, we're actually able to see that console log that we put in our cleanup, or in our canceller function here. So I, I think that, yeah, it unintentionally made this example slightly more complicated. Basically, when you fork a fiber, that fiber, if the way that run fork works down here, that fiber may not have like fully started by the time our program's done. So yield now basically allows me to yield execution back to the fiber that I forked in order to make sure that that's actually executed. For the APIs that we have in platform node, I think, keep me honest, you two, I think that the platform node runtime makes sure that if we fork a fiber, we actually have the ability to execute it. But the yield now in this case, like if I remove this, you'll see that we don't get that interrupted log because that fiber hasn't even had the chance to like start executing by the time our program's actually done. Does that make sense? Let's try. I actually don't know. Yeah, I don't think so. I think the whole thing here is that when we've forked a fiber, we have that execution running, but in what's happening here is we're not ever actually, a better way to do this probably would be to remove the fork, or you could explicitly join the fiber later. So if you were to join the fiber later in this program, like we wouldn't need to yield now. The yield now is unintentionally complicating this example, so I apologize. Yeah, so maybe let's do exactly that and make this a little bit simpler. That like in this case, the logs disappeared. In this case, the log should be there. Obviously, we get an error because our program was interrupted, but we still get the like cleanup being executed. So again, my apologies for unintentionally complicating this very simple example. It doesn't throw necessarily, it effect.fails with a timeout exception, yeah. And you'll see it in the error channel. Like you can actually recover from a timeout exception if you need to. Other questions? We have another exercise that's related to async. So if there are no other questions about normal async, effect.async, okay. So with multi-shot callbacks, we can actually leverage the stream.async methods. So obviously with single shot callbacks, those are like, exactly that, single shot. The whole streaming API that we provide with effect is designed to handle multi-shot effects, or effects that can be executed many times. So if we have a multi-shot callback, for example, like an event emitter here, this is a very dumb example, but I tried to make it simple. If we have an event emitter, for example, that can emit many events over time, we can utilize the stream.async set of combinators to basically do the same thing, wrap these asynchronous callbacks, but allow us to resume with some information in that stream. So in this case, in the stream.async combinators, we actually get an emit data type instead of just a resumption function. And emit has some helper methods on it that allow us to do some useful stuff with stream, basically like convenience methods. So here we're just using emit.single. But let's say that your stream.async returns like a list of results. For example, if you have some multi-shot callback API that emits batches, right? You can use emit.chunk, there's emit.fail, there's emit.succeed. So there's like a bunch of helper methods on that emit data type that allow for basically getting data back into your stream that are just there for convenience. In this case, we're just using emit.single because we're getting one event at a time. But because it's a multi-shot callback, we're using stream.async instead of effect.async. So let's take a quick peek. We have one additional stream.async method because we can actually with stream.async, we also have access to stream.async scoped, which is useful when you're importing an asynchronous callback that requires some scoped effect. So imagine there's actually a exercise that we definitely won't get to, but you guys can practice it if you want to. Imagine you have some API that you want to integrate in a streaming fashion that needs a scoped resource. The exercise in question that I'm talking about is integrating with a file watching API that needs to set up and then tear down that internal subscription to the file system. You can actually use stream.async scoped to have a scoped effect inside your call to stream.async scoped and still have access to that emit method to allow you to emit data into the stream. If you want to see an example of that, or if you want to try the exercise yourself at some point, I'll point out the exercise at the end of this session that we probably won't have time for. But that additional method on stream is useful for when we have a scoped resource that we also want to import into a stream. So taking a step back to a little bit more simple, let's actually implement ourselves this capture events method. So we'll take the stream.async family of constructors and we'll try to import an asynchronous callback into a stream. We take an event emitter and an event name, and we should handle pushing successful event emissions into our stream and fail the stream if there's an emission error. So in our exercises, you'll see under session 1, there's exercise 1, all set up for you to get started. So let's take maybe 10 minutes again and try to implement this ourselves. And again, raise your hands if there's questions. I'll be walking around. So why don't we pick things up again, just since we're running a tiny bit ahead of schedule, and if there's questions, we can address them. Let's take a look at the solution. So somewhat similar to what we saw on the slide, although in this case we're obviously handling the emission errors as well. But the point here is to basically take a look at, we have some event emitter that we want to wrap with a stream.async. This is a multi-shot callback that we want to import into a stream. So we're receiving the emitter itself and the event name as arguments. We can wrap that in a stream.async call directly. There's no resourceful operation here. We don't really need any effectful operations to do this. So we can wrap this directly in a stream.async. Sorry, was there a question? Raise your hand if there's questions while I'm talking, and also shout at me if I don't see you. So if we get an error, we can again use this emit data type here to help us and directly fail with that error. And if there's a value that we get back, we can use emit.single to just emit that individual value. I'll quickly highlight that there are a bunch of methods on the emit data type that are helpful. So emit.chunk is useful again for situations where these callback APIs may be batched, so you may be getting a list of results coming back from that callback. So you can pass that on directly to emit.chunk. There's also a bunch of other helper methods in here to try to help with situations where you may want to die with the result of some failure. You have a message that you want to pass along with that unrecoverable error. If the stream is done, you can directly signal that with this emit data type. We should probably change the name of halt to interrupt, but you can interrupt the stream. You can use from effect and from effect chunk to basically return effects directly from these methods. So there's a lot of flexibility with the emit data type. And if we run this example, hang on, I'm going to put the mic down. Say that again. It is, and you can, so it is, because why have an object when you can have a function? So emit itself takes an effect. The reason I don't point this out necessarily is because the data type, the effect that it takes may be like somewhat less easy to read than some of the helper methods. And in most cases, you don't necessarily need to call emit directly. But emit is a function as well that has these methods attached to it. It takes an effect that gets either a chunk or an option of the error. Signaling with option.none is the same thing as calling emit.done. It's basically just convenience methods over the top of emit. So option.none here basically is end of the stream. Option.sum with the error means that the stream has failed, and so on. So that is good feedback. Actually, can you put that in the Discord, in the advanced effect Discord channel? That's a good point of feedback. Feedback also very much appreciated for the docs. It has been a very iterative process for us. So, any other questions before we just run this really quick? Okay. So the way that this program is set up is it can, it's basically just emitting a bunch of information. I think I have it set up to like randomly fail. So eventually we'll get some failure, but the point here is that we're able to import this event emitter directly into a stream. So now we can work with the stream in effect instead of having to deal with the underlying event emitter. And this kind of pattern of wrapping multi-shot callbacks with stream.async works for any type of multi-shot callback. So hopefully this is a pattern that could become useful for you folks. Are there any other questions about stream.async? If we have time at the end, I will go back to the example that highlights async scoped with stream. But any questions about stream.async itself? Cool. Okay. So again, going back to the list of decision points that I mentioned at the beginning, we've talked about integrating with callback-based APIs that are single shot. We've talked about integrating with callback-based APIs that are multi-shot. We've talked about promise-based APIs, which have very reasonably easy constructors to use. But what about when we get to a situation where we have a callback-based API that's at an execution boundary? So for example, like an effect request handler, where we actually want to like run the effect to completion at that point. But we want to have our express server or request, our HTTP server like wrapped by effect. In situations where we get to an execution boundary, it's often useful to directly access the effect runtime. And when we bring up accessing the runtime directly or creating custom runtimes, it can sound somewhat complex or maybe a little bit intimidating. But I'm here to tell you that the runtime is an extremely simple data type. All a runtime is it's just a object that has the context that you've built for your effect app, a fiber refs data type, which is basically used to carry all the fiber refs in your effect app across different fiber boundaries, and a set of runtime flags. Most of the time, you'll never need to touch the runtime flags or the fiber refs or really even the context unless you're building yourself up a custom runtime. And there will be an example of a situation where I needed to modify the runtime directly later. But this is really all a runtime is. It's a collection of these three data types that we can then use to actually execute the fiber itself, like run an effect on a fiber with this runtime data type. We are not going to have an exercise yet because the session project will involve utilizing the runtime directly, the effect runtime directly. And instead, we're going to briefly take a look at the scope data type because I think while most of us are familiar with the basic scope data type, right? It's the foundation of resource management with effect. It's very useful for conceptualizing effects that have resources with some lifetime, right? You had mentioned before, when we have some resource that we want to manage with effect, we can use the different resource management APIs that we have in effect, like acquire release and things like that, to indicate that our effect requires some scope to be provided to it. We can attach finalizers to scopes, which are basically functions that run when the resource needs to be closed. And we can also close the scope directly if we have a closable scope, which we'll talk about in a moment. But there are other operators on scope that are really useful and extremely powerful, but they don't get as much attention. And these two operators are scope.extend and scope.fork. Scope.extend is literally the foundation for the scoped layers that you can get in effect. So when you create layers in your application, if you've ever used layer.scoped in your effect apps, the foundation for layer.scoped is being able to extend an existing scope to another effect. Well, again, we'll talk about this in a moment. And then you can also fork a child scope off of some parent. So maybe we can get a little bit of a visual of what this looks like. So on the left side of the screen here, we have a parent scope and a child scope that we've created in our effect app. We're acquiring some resource inside the child scope, which adds that a finalizer to release that resource to that child scope. So when that child scope is closed, the finalizer is executed, right? This is very simple, like basic scope management in effect. What's cool about scope.extend is you can manipulate where those finalizers actually get attached. Like what scope are we actually using to provide to our effect, right? So on the right-hand side, we're using scope.extend instead of just using the scope combinators directly. We have a parent scope, and we may or may not have some child scope that wraps the acquisition of this resource, right? There might be a child scope there, there might not be. But if we extend the parent scope, if we for the acquire release that we're performing, if we use scope.extend to extend the parent scope into that resource acquisition, then the finalizer actually gets attached to the parent and not the child, if there's even a child scope present. And what's cool about that is, again, when the parent scope is closed, that's when your finalizers get executed. So again, going back to thinking about layers, this is kind of why having multiple scoped layers works. We build a scope, and we continuously extend it with the layers that you're building with layer.scoped, which basically is the scope that we wrap the point at which you provide your layer. We build a scope and use it to provide to all those layers. Any questions about extending a scope? It can be very useful when you need to manually manage which scope is actually being used for resource acquisition and release of resources, especially if you're operating in a child scope, but you don't necessarily want the acquisition of that resource to be attached to that child scope that you know you're going to be in. And then there's forking a scope. So I mentioned before that we can manually close a scope, which executes all the finalizers that are attached to that scope, right? But the only way we can manually close a scope is if we have a closable scope. And when we, the only way to get access to a closable scope, there are a couple, but the easiest way in an effect app is to fork the parent scope that we're already within. That gives us access to a child closable scope, which we can attach resources to. And then we can either, you can see here, manually scope.close that child, which executes the child finalizers, or we can allow the, this is actually somewhat incorrect, but when that child scope closes, we can basically execute the parent and child finalizers. So these two scope operations can be really useful if you need to manage scoped resources in a very granular way. Most of the time, you really won't need to drop down to this level, but it can be really useful for managing scopes directly if you need to. Any questions? So we're going to take the last half hour of this session, and we're going to do a session project where we're going to take a bunch of the stuff that we've already learned and try to build a simple Express REST API, perform some CRUD operations, and the project itself is going to be divided into 3 stages. Stage 1, which we're going to do right now, is to actually build up the Express server. So we're going to implement the listening functionality of our Express server. Our implementation should utilize the Express service to gain access to the Express application. This will make sense when I flip over to the code. Properly manage the opening and closing of the Express server itself. And as a slight wrinkle that I'm throwing into this, when you actually execute the listen method on the Express server, we should utilize effect.log to run some message, to log some message to the console that maybe indicates what port we're listening on. So not a console.log, and we want to use the effect.log combinator to do this. And as a hint, to be able to execute that effect.log inside that listen callback, which is an execution boundary, we might consider accessing the underlying runtime and utilizing that. So if we flip over to the code, in session 1, not in the solutions, there is a project file, which again is divided into 3 stages. And if you scroll down past the instructions, the server live layer is where we're going to implement stage 1. So you guys can delete the existing code in here. I was just trying to minimize the number of type errors we were getting. But see if you guys can build up an Express server, properly manage the lifecycle of that Express server, and then log using effect.log what port we're listening on. And again, we're using a layer to basically we're using a layer to do this, so you don't have to implement the layer functionality itself. You can focus on implementing the actual Express server. If there are questions, just raise your hand, I'll come by. Let's take a look at the solution for stage 1. So this was good feedback for the future, but if we take a look at the solution that I've come up with here, there are a couple things going on here that I want to point out. So the first thing is I apologize that there was that the context tag for effect was a little bit buried in the file. That's my fault for not putting it in a better location. But all that Express tag does is creates the Express app itself and returns it, and it attaches body parser in this case. But this is my fault. I should have put this higher up for you folks. But all it does is construct the effect app itself. And then effect has a effect.runtime method, which we can use to grab the existing runtime that effect is currently using to run effects. And then we can basically use that runtime to do stuff, right? In this case, this never is actually not needed anymore. But effect.runtime allows us to access the current runtime. And so if we look at the type here, we have an actual instance of runtime. And like I mentioned, on runtime, we have the context, the fiber refs, and the runtime flags, none of which we need to actually do anything with at this point, but just kind of bringing it back to that image that I showed you. So we are grabbing access to the current runtime. We're currying run fork. We can use run fork directly here if we wanted to, but there are two pieces here that I think are helpful to point out. The first is that we're using an acquire release to actually start the listening functionality of the Express server. And then when we release, we want to close the server. But kind of like the maybe not so straightforward part of this is actually using runtime.runFork to allow us to run effects at execution boundaries. So what this basically does is when the app starts listening, it executes a fiber which runs this effect.log. And again, because this is an execution boundary, we can do it directly with the runtime that we've pulled out of the that we've basically pulled out here. I know this was like not necessarily the most straightforward exercise, but I think it's useful to get an idea of how you can grab like the existing runtime that effect is using and potentially use it to run effects at different execution boundaries within the context of your current effect application. We can move on to the second stage of the exercise, which is basically to build the first route here. So I've set up a bunch of different routes. We don't have to get to every single one in the time that we have left, because I think we only have like 10 minutes. Because stage 3 would just be to like implement the rest of the routes. But why don't we take a stab at least implementing the to-dos ID route. So we're basically going to finish the implementation of the layer, which adds the to-dos ID route to our application. If the to-do is found, we can return the to-do as JSON. If the to-do is not found, we can return a 404 along with the message that the to-do was not found. Again, if you want, you can try to use, now that you've kind of seen how we can utilize runtime to do this, you can try your hand at using runtime. And then when we circle back to talk about the solution, the way that I implemented it, we'll also talk about, since we won't get to the last part, we'll talk about fiber set as well, which is a data type that Tim implemented to make doing some of this fiber management a little bit easier. So why don't you guys give this a shot? And again, raise your hands, we'll come around, we'll try to answer questions as best we can. So let's take a quick peek at the in this get to do route, there are a couple things going on. The first I'll point out is that I'm utilizing a fiber set, which is a data type that actually Tim worked on recently that makes doing certain runtime related operations a little bit easier because it manages the fiber for you. But you could just as easily use a runtime here for what you need to do. This is really just for example purposes. But all we're really doing here is grabbing the ID off the request and then utilizing our to-do repository to get the particular to-do, matching on the result, and returning something from our effect API, from our Express API when necessary. And then at the very bottom, we actually use run fork to execute this program. And again, in this case, the fiber set is not necessarily required. We could use a runtime to do this, but it kind of exemplifies. And maybe Tim could provide a few comments on like other situations where like fiber sets might be useful. But before we talk about that, I just want to see if there's any questions. I want to respect the break. And I'll also quickly mention that this Express app that we built here is not at all the proper way to actually wrap an Express server. This is all for example purposes. If we were to do this in a like library sense, in like building up an Express integration for effect, there's actually an example of the proper way to do it. In the solutions directory, there's a file called advanced that shows the actual way to properly integrate with the Express API in like a library sense, to basically make like the external library easier for consumers to use. Because technically the way that we're doing it right now, if we go back to like the examples of what I was saying, like you can do one-offs, you can do like an all-in on effect, you can do flexible in terms of like your integrations. I would actually consider what we're doing right here very like one-off, because we're creating like a whole separate layer for each route, and we're not, it's kind of like a little bit verbose. But in that advanced file, you can kind of get an idea of, if you leverage a lot of the internals of Effect, how you can provide like a better library experience if you were to build up an Express app. Any questions? And then I'll give Tim 2 seconds to talk about FiberSet here. Sure.
Sorry. Just a general question. What's the benefit of doing it this way rather than, for example, just creating an effect that appears to do with just do run promise? Here I see we're sort of creating a layer, or almost like push, instead of pulling requirements in and creating a layer and then pushing it into the effect servers. I sort of see it.
It goes back to what Tim said before, where if we were to just like run on this, you're saying if on this program, if we were to directly just like run promise?
Yeah, like instead of, you know, if we take a traditional Express app.
Sure. So if we were to directly take this and do like an effect.run promise on it, the problem is that, as Tim kind of mentioned before, run promise, not promise, right? If we were to do this, the problem is we would need to pass all of our context through again, whether like if we're building up layers or things like that that are accessed by our program, that would all have to get passed through again, because effect.run promise is just going to run the effect that you give it. By utilizing a custom runtime, we can pull the runtime that's executing outside of this Express handler, right? If we were to just, instead of using a FiberSet here, if we were to use a runtime, the same thing, the runtime is going to have all the context that's being used to build this effect app outside. So you don't actually need to do things like providing all your layers again and reconstructing all the layers. Because if we used run promise and passed all our layers through here, every time we hit that route, we're reconstructing all those layers. We're going to lose a lot of context. It becomes expensive. So this is a way to kind of allow, at execution boundaries, the preservation of context we've already built up, runtime flags that we've already turned on or off, fiber refs that we may or may not have set. I know we're over. I'm sorry. So yeah, and then Tim, if you want to give like a 1 minute, so that everybody can have 10 minutes. We're all hungry.
So if we looked at the runtime example earlier, we were creating the runtime using run fork. But there is one problem with that, is if, let's say, the request is aborted or we shut down the server, those fibers will continue to run in the background. So if you had a request that took a minute to execute, but you wanted to make sure that shuts down when your server is closed, you would then have to go a step further and make sure like the fiber is interrupted when the server is shut down, which is a little bit complicated. So what FiberSet does is essentially the same thing as the runtime example earlier, but it's actually a scoped resource. So if you look at the signature, it's adding a scope. So when that scope is closed, it ensures that all the fibers are shut down in that set. So if you use that run fork function, and you run an effect, if that fiber set is shut down, that fiber will also be shut down. So it kind of adds resource safety on top of runtime and a more easy to use API. So hopefully that makes sense if you had a quick question.
Not creating or is it inheriting the?
So this is make runtime is a convenience constructor. If you use FiberSet.make, you get like the full, you get that actual FiberSet back, which you can add fibers to manually, or you can add fibers to manually, or you can delete fibers from a set, or that kind of thing. But what make runtime does is takes that fiber set and gives you back like a run fork function that you can then use easily in kind of like your execution boundaries. So it's the same thing as calling FiberSet.make and then using the FiberSet.run function, but all wraps up nicely.
Have you considered making this the default runtime? Because sounds like people will be confused.
You can do something similar with the default runtime, but you have to manage the scope yourself and then pass it into the run
Yes,
for.
so I'm asking like maybe like the runtime dot, I mean the fact that runtime should return 100%.
There are situations where you don't want to do that and you just want the runtime itself back.
There's actually an example that we're going to have later on where we don't want like to create a fiber set, where we actually just want to construct a runtime and literally turn off one runtime flag. We'll see it in session 4 later, where like we're going to be using metrics, but by default the metrics API like turns on a bunch of like fiber related metrics, but to like make the output cleaner for us to look at later, we turn off that flag. So the runtime API is like the lowest level we go, and it's kept simple intentionally in case you want to do things like that, which wouldn't be possible necessarily with a fiber set. So I think keeping like that low level API is important to make just doing those simple operations on a runtime easier. Sorry, Tim. All right, let's take a break. We'll resume in about 10 minutes. Thank you all for your attention, and yeah, see you guys in a little bit. All right, folks. Think we'll try to get started again. So in this session of the workshop, we're going to be focusing very heavily on the fiber itself. So in effect, as many of you know, a fiber is what we basically construct in order to run the effects that our effect programs. They represent a handle to our running computations. And oftentimes, there are situations where we want to synchronize or coordinate between multiple fibers running in our effect applications. We've already seen some examples in session 1 of utilizing fibers to do different things. But in this session, we're going to dive very deep into different strategies that we have for coordinating fibers, trying to synchronize them, and executing work across multiple different fibers. We're going to take it slowly. So if we don't make it to the session project, that's okay. Everything's available for you, open source, online. All the solutions are there as well. So we're going to take our time, try to answer as many questions as we can. But let's dive in a little bit. So I think that in effect, probably one of the most not inside effect itself, but in the effect community, in effect applications, I think one of the most underappreciated data types that we have is deferred. So deferred, it's a very simple data type. It's a purely functional synchronization primitive that we have in effect. And all it is a representation of a single value that may or may not yet be available. So oftentimes people draw parallels to like a JavaScript promise, although the semantics are not entirely the same. But if we take a look at the data type semantics of a deferred always starts empty. It can be completed exactly once at some point in the future. And after it's completed, it's unalterable. We can't change the value of a deferred after we've completed the deferred. But why is it useful for fiber synchronization or coordination? Or why are we even talking about deferred in the context of fibers at all? So deferred is extremely useful for basically forcing fibers to wait for something to happen elsewhere in an effect application. And we can propagate information between fibers with deferred as well. So maybe we can take a look at an example here. I know the code might be a tiny bit small, so maybe I can pull it up in the samples directory. Here. So in order to create a deferred, we can use the deferred.make constructor, right? This gives us back it's an effectful operation because we're creating mutable resources under the hood. So deferred.make is an effectful operation that we're performing. So we need to either yield that effect or run it somehow. So if we're in a generator, yielding it is a very easy way to create a deferred. And when we make a deferred, we have to indicate how we are going to be able to complete this deferred later. So we need to give it the value, the success value that it could potentially be completed with later. as well as the error type that it could potentially be completed with later, because deferreds can be completed both successfully as well as we can fail deferreds. In this case, right here, we are creating a deferred, which we're saying can never fail and be succeeded at some point in the future with a string, right? And that's very clearly indicated in the signature here. We have a deferred with a value type of string and an error type of never. What this example here is showing is we are forking two different fibers in this example, right? In the first piece of code here, we are forking a fiber which is basically going to wait for that deferred to be completed. So we're using the deferred.await method to indicate that this fiber should be suspended until we get the value of the deferred back. But what does it actually mean to suspend a fiber, right? We talk about it a lot. We say, oh, I'm going to suspend this fiber is yielding to another. What does that really mean? If we want to just not get too jargony and think about it conceptually, when we suspend a fiber, we're saying, okay, we're going to pause execution and let other fibers run, right? We're saying the fiber should stop here, wait, and let other fibers go ahead and run. If we think about it very not technically, right? Just trying to grok what's happening when we say we suspend a fiber. So deferred.await says, hey, suspend this fiber, pause execution of this fiber, yield to other fibers, let other fibers run, until we get a value for this deferred back, right? So what's essentially happening here is we're waiting for the deferred to finish, and once it's finished, we'll get this log immediately, because it's happening before we await the deferred on the fiber. So this effect operation runs. Then we wait for the deferred to be finished, and only once it's finished will the fiber be able to continue executing and run the second log that indicates that our deferred has been completed. We're utilizing effect.fork to create this fiber, and yielding this gives us back a runtime fiber, which is essentially a handle to that running computation, right? We've forked this fiber, we've constructed the fiber, the program is, this program that we've specified here is running within that runtime fiber. And so now we have a handle to that running fiber. In another fiber here, we're saying, okay, we're going to go ahead and succeed this deferred, right? And we know that we can only succeed it with a string because we've indicated that in the constructor up here. So if I were to change this value to a number or something, which I'll show in a second, we'd get a type error. We're saying we're going to succeed the deferred. We're going ahead and doing the operation of saying, hey, go ahead and succeed this deferred with the value of hello world. But we're doing that after a second. We're waiting a second to actually complete that deferred. So what this example shows is this fiber up here is going to wait a full second for this deferred to be completed before we actually get this log. So we've got two computations running in two separate fibers, but they're synchronized on that deferred, right? The deferred allows us to synchronize those two fibers, and we get the benefit of also being able to propagate the value that we're succeeding or failing the deferred with across those fiber boundaries. So the fiber that we're getting back here, if you notice, can actually succeed with a string, and it can never fail, which is the exact same signature that we have in the deferred, because the awaiting a deferred returns its value, right? Any questions so far?
Why do we need to sit right?
Because this whole computation is being forked into a fiber. So if you were to directly yield each one of these operations, those would all be happening on the parent fiber, which is running this effect.gen. And actually, that's probably a good point. I should point out that the program that we're running here has a parent fiber, which is forking two children, right? We have this fiber here, which is child number 1, and this one here, which is child number 2. And I actually have a picture of it. You can see my diagramming skills in a moment. I'm sorry if the text is small. The picture is what's more important. We've got this parent fiber sitting on top of everything, right? Maybe I can zoom in. Can I zoom in? Sorry. We've got a parent fiber sitting on top, which is where we actually construct the deferred, right? That's where deferred.make happens in our effect.gen. We then fork a child fiber, which is actually doing the work of awaiting that deferred, right? Which is seen in this example. We have a second fiber that we've now created, which is actually doing the work of awaiting that deferred. And then after we've constructed the first fiber, we have a second fiber that we fork, fiber number 2 in this example, which performs the delay and then succeeds the deferred after a second, which propagates the result back to fiber number 1 and allows it to then continue. So this dotted arrow kind of says, okay, we're suspended until the deferred completes. So if we go back to our code example, the reason why we can't directly yield this deferred.await and effect.log and everything like that is because then everything would be happening on the parent fiber and everything would happen sequentially. Well, that's what I'm saying is that we could run an effect.gen in this yield call, but like we could run an effect.gen in that yield, but everything what we're passing to effect.fork is the program that we want to execute in a separate fiber. So this yield here, we could turn this into an effect.gen and maybe that would be clearer. And for those of you unfamiliar with zip right and zip left, this is essentially the same as flat map without the thunk, right? So I could turn this into a flat map. And zip left basically says run this, but return this. They're just two helper methods for doing different sequential operations. And I tend to use these instead of like end then and flat map if I don't need like the thunk or anything like that. That's actually really a much better way to put it. It's tap without the thunk. Yes, maybe. I think the reason why we call it zip left is because if you write this in not a piped fashion and you have the left effect and the right effect, like without using like the dual API, like the left side is what gets returned. So like if you run it as like, you pass both effects in next to one another, the left side is what comes back. But maybe we could come up with a better name. We're always open to suggestions on naming. Naming is extremely difficult, especially when you have as many combinators as we do. So what is this basically like doing, right? We have the reason why this is important is because many of the synchronization primitives that we have in effect are built upon the shoulders of deferred. Q, the entire Q data type is built upon the shoulders of deferred. A lot of the other synchronization work primitives that we have in effect are built upon the deferred data type, which is why I say it doesn't get as much love as it probably should. It's a very simple but very powerful idea. And if we run this example, maybe we can show a little bit better what happens. And session. Oops, make this terminal. Pull it up here. Let's get rid of this one. So the logs may be a little smushed here, but what's cool here is, again, you can see we're in fiber number 1 right now. So if we go back to that, fiber 0 is the parent fiber, the one running the effect.gen in this case. Fiber number 1 is the one that we're forking to wait on the deferred to complete, right? Fiber number 2, after a full second, right, at 42 here, succeeds the deferred. And then on fiber number 1, we get a message saying the deferred is complete, again, after a second, right? And maybe if I made the wait longer, it would be easier to see this. But basically, if you look at the timestamps, you can see in fiber number 1, we paused execution, yielded to fiber number 2 to actually run operations. And then when fiber number 1 resumed, after the deferred was complete, it was able to log its message and proceed. And I put in this other console log here to basically prove that a full second elapsed in this program. So we basically have when we join this fiber that we have a handle to up here, I proved that we're waiting at least a full second just using the console time API. But what's the powerful concept here is we have two fibers running in parallel, concurrently, right? We've got two concurrent programs running and yielding to one another cooperatively. And the deferred is what allows us to synchronize them. Any questions about this? Sure.
In a lot of internal, we don't see the hello world.
Because I'm not logging it. No, I don't think so. Oh, am I? Let's see. Interesting. Oh, there we go. Maybe it got cut off before when I was moving my terminal around. I'm not sure. Yeah.
If you install the time, like the Node.js PI for logging, but like an effect for it, will we see like 5.0 being logged? Like you mentioned like there were 3.
Oh, yeah. Yeah, here, wait. We can. Did I just? Sorry, my microphone turned red. I don't know if that means it's running low on battery. So you can see I just adjusted the console log that's happening directly in the effect.gen, and you can see that's happening on fiber 0. So again, any other questions about this, by the way? This is kind of like the foundation for the rest of this session, so I want to make sure. So deferred is super powerful. You can build tons of synchronization primitives on top of its shoulders. We'll talk about some of them too, and we'll also talk about some design patterns which are extremely common in effect that utilize deferred. We use them a ton for libraries that we develop, and hopefully we can pass those patterns on to you folks to use in your applications as well. And I will also note, I haven't published the slides in the repo yet because I was adjusting them as early as this morning. But I will be publishing a PDF of the slides after the workshop as well in the repository. So everything about this will be open source. So let's do a quick exercise with deferred to try to again, maybe grok this a little bit better. The goal of this exercise is to explore how we can use deferred to propagate results between fibers. So remember, I mentioned that when we await a deferred, we're awaiting its result, right? And when we construct the deferred, we say it can succeed with X and it can fail with Y, right? The requirements of this exercise are to propagate the full result of maybe fail, which is in the exercise file, which I'll show you in a second, from the child fiber back into the parent. And we should avoid utilizing the easy way out, which is effect out into deferred. Effect has a built-in combinator to basically take a deferred and create an effect which the success value of the effect is the success value of awaiting that deferred, and the failure value of the effect is the failure value of awaiting. Basically takes the result of the deferred and lifts it into an effect, like awaiting a deferred, if that makes sense. So if we take a look at the exercise file really quick, and if anything about what I'm saying is unclear, please stop me and ask questions. If we look at exercise 0 here, we have this maybe fail, right? Which we're using the random service in effect to get a next number. And we're using filter or fail to say if that number is greater than 0.5, we're going to fail. Excuse me. And then if we fail with n. In this program here, your goal is to take this deferred that we're constructing and implement the logic to propagate its full result back to the parent fiber, which in this case is the fiber that's running the effect.gen, right? So I've done the work of putting the effect.fork in here. Your job is to implement the logic. And you can see that we're on the parent fiber here awaiting the result of that deferred, which is in a child fiber, okay? All right, I'll give you guys a little bit of time and I'll walk around. So I think most people arrived at a solution that at least propagates failures and success values across fiber boundaries with this, which is great, right? This is, I think, the solution that a lot of folks ended up with, just matching on the effect, failing the deferred with an error, or succeeding with the value if necessary. But there are a couple of problems with this implementation. Remember, a deferred can propagate the full result of an effect across fiber boundaries, right? And at the moment, this solution does not handle defects or interrupts, right? We could handle defects simply by changing this match effect to a match cause effect, right? And then this error actually becomes a cause. We can fail cause. And Tim, correct me for a moment. Does this handle interruption now? Right. I didn't think so. So this will at least allow us to handle defects, but if I scroll down, we also want to handle cases where the deferred is interrupted, right? Because when you await a deferred, that fiber is going to, I actually got a really good question about this from this side of the room. When you await a deferred, does that ever time out? And the answer to that is no. If you have a deferred waiting, if you are awaiting the result of a deferred in a fiber, that operation will never time out. It'll go on forever until you terminate your program. So if that deferred never gets completed, that fiber will just wait forever. So that's the other reason why you see me forking the await into child fibers when it's not like when I'm completing the deferred, how do I say this? If I were to await the deferred in a fiber and complete it later on the same fiber, I'd never arrive at that completion. If everything's happening in that same fiber, because all we're going to do is we're going to sit there waiting for the result, but we're never going to allow that fiber to proceed to the instruction to actually complete that deferred. And the reason why I'm bringing that up is because you'll see oftentimes us forking the deferred and then completing it elsewhere, and those semantics are things to be aware of. Here, we're using effect.onInterrupt to manually propagate the interruption signal back to the parent as well. Because just doing match effect or even just match cause effect, as Tim pointed out, we're still not handling that case for interruption. So, in summary, and then I put in one last implementation which we could use here. Does the exit implementation propagate interruption?
You have to use on.
Right. So the one last way we could do this, which might be like the shortest implementation, is using effect.onExit and then completing the deferred with the exit value that's received by onExit. There's a bunch of different ways that you could do this. But what I'm trying to point out here is that if we want to make sure the full cause of the deferred is propagated between fiber boundaries, we need to handle all of these different cases: success, failure, defects, interruption, right? Those are kind of the things that you should be keeping in mind when you're thinking about synchronizing fibers. Those 4 things: success, failure, defects, interruption, always. So you can play around with this example. I had some other code that I put in here, but I think that we've kind of belabored the point now. Deferred is great for synchronizing 2 different fibers, but making sure that you properly synchronize them is somewhat not challenging, but it requires attention to detail, because deferred is like a low-level primitive for synchronization. Okay, so now let's talk about queue. We're building up to a particular pattern that I think is very useful in effect. So first we need to talk about queue. Queue is a lightweight in-memory, fully asynchronous way to queue up elements. We can transparently backpressure using queue, and it builds upon deferred, which we mentioned earlier. It's got 2 fundamental operations. I think most people are aware of this, so I'm not going to belabor this point. We've got different queue constructors, which have different semantics. Unbounded queues, where we can just keep adding elements in an unbounded fashion. Bounded queues, which will backpressure elements. So in this case, we've got a bounded queue of size 4, so we'll end up backpressuring elements which attempt to be added to the queue. We got sliding queues, which will drop elements from the front of the queue if we're adding elements past its capacity. And then we have dropping queues, which if the queue is full, will just drop elements as we're working. So the reason why I'm bringing up queue is because we're not going to do the coding exercise just quite yet. I want to make a few points. Queue is extremely useful for distributing work between fibers. So we've talked about how deferred can propagate results. Queue is really useful for allowing us to distribute work between multiple fibers. In the exercise that we're going to do in just a moment, we're going to work to create 3 separate implementations of a worker fiber that take values from a queue that we're constructing and perform some work on that value. So before we dive into the exercise, let's take a look at it for a moment. I told you we're going to take our time. So this is the solution, which we do not want to show you. And then this is the exercise. Okay. So we're going to create 3 separate implementations of workers that take values from a queue and do some work. The work that we're going to do here is just do some work. It's simulating performing some non-trivial work. So we're going to consume values. These values are going to get passed in. And then, we're delaying for 20 milliseconds, which, again, just like some non-trivial work that we're trying to do. In the exercise, we're creating an unbounded queue, just for simplicity purposes. And we're going to be constantly offering every 1 second, we're going to be offering the numbers 0 through 100 to that queue. That's going to be happening in a forked fiber. So every second, 100, 0 through 100 will be added to that queue. Your job is to finish each of the subsequent implementations where we're creating fibers that pull work off of that queue, right, and do some work. In the first implementation, we want to pull work off of that queue sequentially, right? So pull work off the queue, produce some work, and we're going to do everything sequentially. In the second implementation, we're going to take elements from the queue and perform work with unbounded concurrency. And in the third implementation, we're going to have some concurrency limit where we only want up to 4 fibers running at the same time to pull work off this queue. The reason why this exercise is even happening, the reason why we're doing this, is because it illustrates the point that in one fiber, we can offer elements into a queue, and then in multiple separate fibers, we can actually pull information off and do work. So we can have all of these operations happening concurrently in separate fibers. And the reason why this is important is because when we talk in the next section about combining deferred and queue together, we'll kind of get an idea of like how we can implement some like really useful patterns. Before we start this exercise, are there any questions on like what I'm asking you guys to do? And if not, feel free to get started. So just to make sure we have time to go over the third piece of this, I don't think we'll get to the session project, which is totally fine, but I do want to make sure we at least get to the third piece of like the pattern that we're building up to. So let's talk a little bit about this. In implementation 1, we want to sequentially pull in work off the queue and do some work on it, right? So all we have to do here is do a queue.take to grab an item off the queue, flat map that to doing some work, and running that forever. So the important thing here, I got this question a lot, and I think it was actually a really great question for all those that asked this particular question. But in effect, the equivalent of like a while one that respects cooperative yielding between fibers is the combinator called effect.forever, which runs the same program over and over and over and over and over again. But in between each invocation of the program, it will yield to other fibers. So that's the helpful piece here to keep in mind, is if we were to run just like a while loop or something like that, that continuously pulled items off the queue, this would drain the queue every time. Like we wouldn't really be able to necessarily have three separate implementations running at the same time. So having the effect.forever here is useful because we can yield to other fibers in between each queue.take. Does that make sense? Under the hood, effect.forever is literally program, effect.yield, flat map to yield now, flat map back to program. So it runs the same thing over and over again, but between each invocation it yields. Cool? Okay. For implementation number 2, for unbounded concurrency, this basically means we want to spin up as many fibers as we want, forever, right? Totally unbounded, spin up as many fibers as we want, just keep going. And, so in this case, we can adjust our sequential implementation, just flat map to an effect.fork, and keep doing that forever. And we'll end up with tons and tons of fibers that we spin up, but we still get the cooperative yielding with effect.forever, right? So we still have the ability to run these 3 programs concurrently. And then, this was kind of maybe like the trickiest one. For bounded concurrency, there's a couple of different ways to do this. This is just like the most concise way I could find. There are a couple of ways to do this. But we basically do the sequential implementation and replicate it n number of times. And doing that will basically allow us to have n numbers of fibers, n fibers running, doing that work. What's, I think, kind of cool about this little example is if we run it. Let me put this down.
Will it wait for the entire form to finish? Or running the effect?
Will it wait? Say that one more time.
So
if I understood you, it's kind of a good question, but I think it's a great question. Like, I think people probably have similar thoughts in their head. Will effect.fork wait for the fork to finish before it proceeds? I think is kind of like what you were getting at.
Wait for the entire fork runs to finish. Like you have the 4 effects, right? But you create 4 effects.
Yeah. Okay. So if we run this, the logs actually kind of give an idea of what's going on. So I'm going to pause this, and we can take a look here. So if we scroll up to the beginning, 100 is probably a lot, but I think it exemplifies this nicely. So the first thing that we do is we end up consuming a single value from the sequential fiber, right? The sequential fiber takes a single value off the queue, and then because it's running forever, we end up yielding to the other fiber that is running, which is the the bounded implementation. The bounded implementation we set at a concurrency limit of 4. So we end up taking 4 elements in a bounded fashion. And you can see with the log annotations here that that's running on the 4 different bounded fibers. And the cool thing is this fiber 11, 12, 13, 14, those fiber IDs will be the same time every time this program loops through. So we'll end up, you basically have the same 4 fibers processing work. So you can think of it like a worker. I hesitate to use this word, but like a worker pool, right? You have X number of workers pulling information off that queue. And then the unbounded concurrency, you can see the fiber counter just continuously going up. So in the previous iteration, we got up to something like 200 something. And then in the next iteration, we went all the way up to 300 something. So that's, again, unbounded concurrency. We're spinning up an unbounded number of fibers in that case. But what this illustrates is that we can distribute the work, doing work on elements of a queue across many different fibers and in a concurrent fashion. We just have to keep in mind, is what we're doing going to like drain the queue before we're ready to process elements on another queue? Are we actually doing things concurrently? Or are we accidentally going to starve that queue before we have the chance to process elements on another fiber? Does that make sense? Any questions? Yes.
Are you eventually going to get an out of memory error that's just spinning up more and more and more fibers? Or is it when the individual fibers complete, are they just going to die and release?
It's a good question. I don't know. Do you know? I think that, yeah. And then garbage collection should take care of like the memory that was allocated. So the fiber, I don't think that you'd ever really run you'd ever get out of memory unless you spun up like, you know, some unbounded number of fibers. Like, you know, in this case, the queue is controlling how much work needs to be done. So those fibers have like a chance to finish or whatever. Say that again? Certainly.
One of
Absolutely. If those fibers like never terminate, if you end up with like a bazillion fibers that never terminate, sure, you could eventually run out of memory. But yeah.
more like the replicate effect and like the concurrency.
So replicate effect is just a way to replicate an effect program n number of times. Doing it in an unbounded fashion means that the program is replicated like in an unbounded. It is replicated. Well, it's setting concurrency to unbounded means that as we're iterating through replicating that effect, instead of like doing that sequentially, we do that in a concurrent fashion. The discard true just means that we don't want to get the results. It's the same thing as when you do an effect.forEach and you set discard true. It means you don't want to collect the results of that back into some structure. So with replicate effect, setting discard to true means I want to replicate this program n number of times, but I don't need like an array of those those effect programs coming back to me. I just want to discard them. Well, in this case, it would be like effects that return fibers, but.
And if we're actually like wait for job to be done, like for the next one, or if like the third one finishes first and like the new one will be pulled out in the queue. Sorry.
Can you elaborate a little bit? Mm-hmm.
Let's say like those 4 jobs don't take the same amount of time to finish.
Sure.
Do we always have like 4 workers?
Yep. Yeah. And nope. That's the benefit of running these in separate fibers is like when the work's done, that fiber can pick up more work if it needs to. The way that we've done this here is just to illustrate how you could potentially implement a program that like is cooperatively yielding between multiple fibers and also processing work from the queue in different ways. But if you just do like, if you're just pulling information off a queue and working on it and you set like some concurrency limit like we did here with replicate effect, for example, as soon as the work's done, that fiber is ready to process more work. Yeah.
I think another way of looking at it is like if you had an array of 4 sequential fibers or 4 sequential fiber effects, and then just pass it to effect of all.
Mm-hmm. Yeah, that's maybe like an easier way to visualize it is the way that Tim mentioned. Sure.
There is a way to stop the effect of forever.
Is there do you mean like, is there a way to terminate that? Like, you would have to interrupt, I believe, to stop an effect up forever from running.
Like manually, like effect of interrupt.
Or, you know, any other way that you can interrupt an effect. So it's like time out the operation after like X number of seconds, and then you can recover from that timeout, or, right? I think interruption would be the only way you could really get out of an effect up forever loop. Or if it fails, that's another good point. Yeah. But as long as that work is being done successfully and not returning errors, then it's like a while one loop. Yeah.
So in this case, we'll just continue.
Each one of these fibers that we're forking, each one of the fibers that we're forking at the bottom here will just continue indefinitely. Yeah. Yeah.
Is there a way, is there an easy way of hooking this into web workers so you could
Tim. So wait, are you going to be at the conference tomorrow? Okay, I'm going to ask if you can wait till tomorrow. I think that I think there will be a really good answer to that tomorrow.
So I'm trying to replicate this replicate effect with like trying to fork the same effect 4 times, and somehow.
Well, so I think that the implementation that Tim mentioned is probably like maybe an easier way to visualize or think about this. Like if you do an effect.all and fork like 4 times, that still sets up like a concurrent, like 4 separate fibers that can process work, right? An effect.fork is an effectful operation. So I'm not exactly sure. I can take a look at your implementation at the break, and we can maybe talk about it. But keep in mind that like forking an effect is also an effectful operation that returns the runtime fiber as well. So, any other questions? Yeah,
I think I'm probably still thinking about it.
that's okay.
But with the fiber IDs, they're just gonna keep going and open up and up and up. They ever reused when the fiber dies.
No, fiber IDs are constantly incremented as you spin up new fibers. In the worker pool example, we have a set number. We have like, you can see it in the logs here. We have like 4 fibers that are constantly processing work, so those always have the same IDs. But if we're using unbounded concurrency, then the fiber IDs will always be incremented. Any more questions? Cool. So I want to talk with the time that we have left about a pattern that is used. I've mentioned this a couple of times, like almost ubiquitously throughout the effect packages, the library itself, and that is utilizing queue and deferred together. So having a queue of items that include a deferred somewhere in the elements of that queue, whether it's literally a queue of deferred or a queue of elements that have some deferred in them. And the reason why this pattern is so useful is because sometimes distributing work to different fibers can be problematic. So for example, what if in the implementation that we worked on just before, what if we want access to the results that come back in some other fiber to then like do some further processing, right? So like what if we wanted access to the results of do some work to then do some more work? I don't know. In the implementation that we had before, it's actually quite difficult to do that. But if we include a deferred alongside the elements of our queue, we can solve this problem by taking from the queue where we want to perform the work, completing the deferred with the result of doing that work, and then awaiting the deferred on another fiber or wherever you need the result of that work. And it sounds like really simple, but this pattern is extremely powerful. It powers for things such as like the rate limiter that we have. I think the original implementation utilized this pattern. Now it does not, but it powers a bunch of different data types that we have in libraries around the effect ecosystem. And it's very simple. Take from the queue, process the element, complete the deferred, and then await the deferred elsewhere. But doing this, we actually get access to the results of these concurrent computations. So we can distribute work across multiple fibers and then wait in elsewhere. It's almost like this is not really a proper way to think about it, but it's almost like a fan in, fan out like operation where we're taking from the queue, doing some work, completing the deferred, and then awaiting it. There is an exercise that we have. What time does this session end? Is it over already? Tell me that's not right. Hang on. Oh, it is over. Okay. My bad, guys. I've done this to you twice now. Listen, I will be available during the break to talk about this pattern that we had just discussed. There is a few more exercises in the session that you can work on at your own leisure. I'm also available on Discord if you guys wanted to collaborate on the exercise like outside of the workshop. But I think learning how to do this will unlock a tremendous number of potential implementations that will give you the power to really leverage the concurrency that Effect provides. So with that, we'll break for now. But again, if you guys have questions or want to ask me questions during the break, feel free. And yeah, thank you guys. So in this session of the workshop, we're going to move to a little bit like of a higher level, maybe, with Effect. And we're going to talk about batching and caching, functionality that's built right into Effect, but perhaps maybe underutilized or not utilized at this point by folks. So I wanted to spend the session talking about why this is useful. We utilize, yeah. Thank you. Perfect. Thank you very much for letting me know. So yeah, request is a data type in Effect that is used by a couple of different libraries now. In essence, it represents a request which we might submit to some data source that can return a value of type A or might fail with an error of type E. And this data type coupled with the request resolver pattern is extremely useful and allows us to do a lot of really cool stuff. I think Tim is going to talk about some of that stuff tomorrow in his talk specifically. But I wanted to touch on how we can leverage request in our own Effect applications to do different things. So it's important to know before we start talking about request that the reason that batching and caching is even possible with request is because when you construct data types that extend the request interface or extend like a request.tagged class, we'll see a couple of different examples. Under the hood, they all implement the equals trait for you. So if you're familiar with Effect's implementation of equals, it's kind of like we've made the equals trait kind of like silent on data types. They don't show through the actual type signature anymore. Specifically, like the data module in Effect no longer really like adds anything to the type signature. But when we implement requests under the hood, they implement equals for us, which allows us to do things like batching and caching. So let's take a look. I know that this is kind of small on the screen, but I wish I could zoom in. Is that really small for you folks in the back? Yeah. Let me see if I have it in the samples directory. I do. I apologize. I'll drop these examples into the samples directory at the break so that you guys can inspect them directly. I am double clicking. Perhaps it's just the way that I've done things has screwed it up. I'm not a front-end developer. But anyways, we'll like I said, I'll take these samples and I'll make sure they end up in the repository for folks to inspect and play with. But in this example here, the first thing you're going to notice is that we're importing data and request. And we're basically trying to build up a request that represents getting a to-do by its identifier, right? So in this example here, we have a to-do which we build using the data.tagged class from the data module in Effect. To-dos have an ID, and they might also have some text associated with them. In the classic example, they'd probably also have like a completed field, but I ran out of space on my slide. It's all right. And then we also have a to-do error, which represents the case where we try to get a to-do by ID, but we have some error that occurs. And this particular piece of data has a message associated with it. So again, and then if we look at the get to do by ID interface, there are two real ways to construct data types that are requests. We can either use interfaces to represent our requests, but it's slightly more verbose than the alternative. But I wanted to show both. So in this example, we use the interface method where we extend request, and we basically specify that our request can succeed with a to-do, or it can fail with a to-do error. And our request itself requires an ID to be passed along with it. So basically, we have a request for a particular to-do ID that can either succeed with a to-do, fail with a to-do error. And when we use the method of extending the request interface, we have a couple of helpers in the effect library that allow us to construct requests. So in this case, I'm using request.tagged to actually make a constructor for getToDoById. I kind of think this pattern is a little bit verbose. We expose it for convenience, but I think the class method is a little bit more concise. Same exact thing, we're setting up a to-do error, and a getToDoById request. But in this case, because classes implement both the type and the data type, we don't really need the whole like extra helper and everything like that. So in this case, we're extending tagged class. We're saying that our to-do, we can fail with a to-do error, we can succeed with a to-do, and we need to pass an ID in with our getToDoById request. Requests themselves are just that. They're just data that represents a request. In order to actually satisfy, to resolve a request for some piece of data, we need to implement a request resolver. In this example here, I have just mocked out the getById method, which is basically saying we pass in some to-do ID, and we either get the to-do back or we get a to-do error. The implementation doesn't really matter. What's important here is the way that we're constructing the request resolver. So there are a bunch of different constructors in the request resolver module that make it really flexible to express like how we're going to actually go about completing these requests. In this case, I'm using probably like one of the easiest constructors to use, which is the FromEffect constructor, which literally allows us to pass to specify the types of requests that we're going to receive. And then resolve that request directly. And I think I have a typo here. This should be getById. That's what I get for updating my slides at the last minute. So basically allows us to resolve that request directly by whatever's returned from this effectful function. So in this case, when we use the FromEffect constructor, I'll call it request accounting is done for us, meaning whatever's returned by getById is how that request will be completed. So if the getById effect here returns a to-do successfully, then that request will be successful and will be a successful request. If it fails, that request will be completed with the error itself. So FromEffect is nice. It makes expressing your requests relatively easy. But the problem with resolving a request using the FromEffect constructor is we don't get to leverage a feature of request resolvers called batching. So batching is something that you can take advantage of with a request resolver if the API that you're requesting or the data source that you're requesting supports batching, meaning passing in multiple, in this case, to-do IDs at once and resolving them all at once. And I have an example on the next slide of how this might look. So again, we have this getByIds method now that instead takes in an array of to-do IDs and returns an array of to-dos to us, or it can fail with a to-do error. But the difference here is I'm now using the makeBatched constructor from the request resolver module. And what's cool about this, again, we take in an array of requests instead, and as long as our API supports batching, like meaning we can pass multiple, in this case, we can pass in multiple to-do IDs, we can leverage the batching in a request resolver. So the complicating factor here is, yes, you get batching, which is really nice through request resolver, but the kind of like maybe annoying thing is that you need to do the, I'll call it again, request accounting yourself. Meaning, in the previous example where we were just using from effect, the effect itself was what we used to complete the request. We didn't have to use any request methods to actually like do anything. In this case, we have to grab all the IDs from the request, call our API to get all the to-dos back, and then for each of the requests that we get in, we need to remap the to-do that we got to the request itself and then succeed the request. So a little bit more accounting that has to be done, but we get batching for free if we just do this little bit of extra work. Does this make sense so far? If anybody has any questions? Yeah. So just in effect.for each is a good question, very good question. In effect.for each, you can pass a couple of different options on the other end as the second argument. One of which being discard, which basically says don't accumulate the results. So if you pass discard false, effect.for each won't accumulate the results into an internal array. Whereas if you don't pass discard, then you'll accumulate all the results into an array. But in this case, we don't actually need to do that because the results, what happens internally here is when you succeed a request, it updates something in the environment that you don't see when you're using a request resolver. So you don't actually need to return the results here. It's basically like a small optimization in this case. Does that make sense? Cool. Excellent question. Deduplication is done for you. Yes. So when you batch multiple requests together, they're deduplicated, if I'm correct, right, Tim? I think we tested this the other day. Yeah. I'm like 99% sure, but we can test it ourselves, like when we look at the example. Because request, like I said before, has implemented equals for you, it's able to deduplicate these like similar requests. So if you pass in 2 requests for the same ID, it will deduplicate that request and you won't end up with like duplicate requests coming through, if that makes sense. So yeah, if you have a complex object that goes along with the request and you want to make sure that you're deduplicating that complex object, like let's say ID is not ID, maybe it's, I don't know, an object itself, right? There's some like other complex object. The easiest way to handle that would be to implement your object with the data module, to express it with data. Because as soon as you do that, again, all of this stuff comes for free, deduplication and caching, which we'll talk about in a minute. So before we move on to the coding exercise, I'll touch on caching really quick. We are going to have an exercise on caching as well. But the other nice thing that request resolvers can provide for you is the ability to cache the results of requests. We're going to talk about it a little bit more in a while, but I at least wanted to mention it that besides deduplicating requests, which we can confirm in a moment, you also have the ability to cache the results of requests across many different invocations. So if we, for example, are running the same request for a to-do over and over and over again, by caching the results of that request with a request resolver, we only actually have to do the computation once. And then every other time we just get the cached result. So we'll talk about caching in a moment. For now, in your, sorry, let me move this over. In your workshop exercises, under session 3, exercise 0, we are going to implement a batched request resolver for the Pokemon API. So you can take a scan through the full file, but basically the following exercise is going to exemplify how we could utilize a request resolver to take advantage of any data source that supports batching requests. For example, the Pokemon GraphQL API, if we take a look at it actually, option, click. Yeah, sure. If we take a look at the console, the get Pokemon by ID GraphQL query here allows specifying a list of IDs, so we can actually batch up multiple requests. And so in our program here, your goal is going to be to implement a make batched constructor for resolving these get Pokemon by ID requests. But I want to take note really quickly at the bottom of the program here that when we actually do an effect.forEach call on the range of Pokemon IDs from 1 to 100, we're going to take a look at the difference in timing between batching the requests and not batching the requests after the fact. Because right now, this implementation right here does not turn on batching for executing these requests. Once you guys have finished implementing your make batched constructor for request resolver, we'll turn on batching and we'll take a look at the difference in time between executing batched versions of those requests versus not batched. A few folks have brought up the default behavior of for each when you don't specify whether you want batching enabled or not. And I think I mistakenly told a few of you that if you enable batching regionally with with request batching equal to true, that will propagate to for each. However, Tim and I were noticing that we are pretty sure that for each by default sets batching to false when we should set it to inherit. So I think we're going to talk with Mike and probably change that behavior, because I think it makes more sense. If you're running a for each and you've enabled batching regionally, you should expect it to propagate into the for each. But we'll talk with Mike and see if he had a reason why we defaulted it to false. The fiber ref itself should default to false, but for those of you who brought that up, that was a really good point. All right. So let's take a look. Did the TV shut off again? So let's take a look at the solution. I'm sorry that I did not handle rate limiting in my implementation of the Pokemon repo. I was not expecting to get rate limited. Silly me. Let's take a look. This was exercise 1. So this was our first exercise, right? This was our first exercise in this session, correct? Yeah, okay. Session 3, exercise 0, basic. So if we look at the implementation here, we basically, for our request resolver, a few of you also brought up the point of the fact that, well, let's go through the implementation and then I'll bring up some points that we could have done differently here. So in the implementation here, we're just grabbing all of the request IDs from the requests, passing them into Pokemon API to get by IDs. You can use find. I chose to use a map and to do the accounting of grabbing associating the Pokemon with its Pokemon ID. And then you can basically succeed each request that comes in. Now, a few of you brought up that maybe we should not assume that even if the request to the API succeeds, that we get all the Pokemon back. Certainly would have solved the issue with everybody not seeing output as we were getting rate limited. So what we could do is we could either handle rate limiting in our Pokemon repo, or we could adjust the request in this case to return an option of Pokemon instead of a Pokemon itself. And in that case, we could instead check if we actually got the appropriate Pokemon back, return an option.sum, otherwise return option.none if we didn't, and that would have also allowed us to see output. A few of you also had questions about error handling here. So request itself has a bunch of combinators on it. Right now, we're just using very simple ones, like request.succeed, and a few of you used request.fail as well. This should be fail. For our error handling scenario, if we have a batched API that fails, that means we probably aren't getting any results back. If the full call to that API failed, which is, I guess, the assumption that I made in this case, we would basically need to handle that error. And we need to propagate that error to every request that came in, right? So every single one of those requests that came in should fail with that same error. So in this case, an easy way to handle that would be if you utilized an effect.gen to handle the logic of completing requests, you could then pipe that gen to a catch-all where you grab the error and then you could fail the request with that error. But again, the point here that this should drive home is that all the request accounting has to be done manually when you're batching. And in order to use batching, the API has to support it. So if you're trying to use batching and your API doesn't support it, you're just still going to end up executing multiple requests against that API, right? Yeah.
You should add that in the specific case that we're having, where you're getting partial results back, along with the option that you can also say like the most naive check, and then figuring out that okay, the lengths don't match, I need to do more work to understand what matches when, and that's when you can get like a more specific failures without fail.
True. Yeah, that would be another way. Instead of returning an option of Pokemon, you could fail in the situation, in the requests that didn't get a Pokemon back that you were expecting to. And then I also wanted to just quickly point out some other implementation detail. Did you have a question? Sorry. Anybody have a question? I thought I saw a hand. No? Okay. I wanted to point out a few other implementation details about how you can actually fire off requests. So in this case, if we scroll down to where the program's actually executing, we are doing a for each on the Pokemon IDs from 1 to 100 and executing repo.getById. And if we look at the implementation of Pokemon repo.getById, we can see that it's taking in this ID and it's calling effect.request, passing in a new request of get Pokemon by ID. And then we also have to provide the resolver that we're going to use to resolve that request. So I will say, in most of the situations where I've used requests and request resolvers, and Datner and Tim can feel free to disagree, but I think that for me, it's been easiest to lift all my resolvers and requests into a service so that I don't have to deal with everything being in different places. I can just expose the API that I want, in this case, get by ID, get a Pokemon by ID, and when I call this particular method, I don't have to worry about passing the correct request resolver. All of that is done within the constructor for the Pokemon repo itself. And there was another question. Did I just lose the mic? Sure did. I will project. There was another question about controlling the batch size coming into a batched request resolver, which was a great question. I forgot that we also have higher order combinators on the request resolver module itself. So if you wanted to control the batch size associated with a particular batched request resolver, you could, for example, pipe this make batched request resolver into a request resolver dot batch n and provided the amount of the actual number of requests that you want to batch at once. So there are higher order combinators that we can use to control the behavior of our request resolvers, which makes it really powerful. It's very highly composable. And there are also other helpers for request resolver that allow you to, for example, if you want to handle multiple requests by a single resolver. So let's say we had get Pokemon by ID and get all Pokemon, whatever. You could use request resolver dot, Tim, what's the name of the function? From effect tagged. And this takes, I think, an object that you pass in your requests and right. So you can imagine, oh, wow. You can imagine if you have multiple. You can imagine if you have multiple different request types that are all tagged you know, if you have like a tagged union that you put all those requests into, you could handle them all at once if you want to. I tend to separate my request resolvers just because sometimes that higher order behavior is helpful. We probably won't have time for the session project, but wait, is this session over? Okay, good. We probably won't get to the session project, but in the experimental package, we have, like, for example, higher order request resolvers like the data loader request resolver, where you can basically pass in an existing request resolver that you have, and then I think it takes a window and a max batch size and basically turns that request resolver into a data loader that batches over a window as well. So the request resolver pattern is very useful. I at least wanted to get you folks used to like writing a resolver, especially a batched one if the API supports it. But the pattern here of pulling all of that into a layer and exposing it as a service, I think is really useful because all that logic is kind of like bundled up into the layer itself. I don't know if Tim or Yuval, if you guys have any other feedback on that.
Can add that this is very useful. The abstraction into a layer is very useful, especially when you're going to test later, or then want to introduce new features or more robust features. Because that's that very thin abstraction of give me an idea, I'll give you a Pokemon without introducing all the complexity of, oh, by the way, I'm batching. Oh, by the way, it's concurrent. Oh, by the way, I'm caching. That allows you to both then reach for testing that don't need to implement all that before, and to then later introduce those features if there would be some program.
Right. So just to point out really quickly, also the issue that we were seeing before. So effect for the for each construct and effect accepts a bunch of different options, one of which being able to enable batching. Because it was such a common thing for us to do, right, batching requests in a for each loop, we decided to put this option here as well. But you can also enable batching regionally. Batching with request batching. True. What the issue that we were describing earlier is basically at the moment, batching defaults to false in a for each loop. So this regional request batching doesn't actually propagate into the for each. What it probably should do is, and we can fix this, is default to inherit, which inherits whatever the regional setting is. So it probably makes more sense to default this to inherit, but we'll talk about it and try to figure that out. And the last thing I'll mention about this is a lot of you like ran this, so you observed like the difference between turning batching on and off. It takes like over 10 seconds to run these queries without batching on. It takes less than a second to run the queries with batching on because obviously all of those Pokemon IDs are going in one request. This request batching combinator essentially sets something called a fiber ref under the hood. And we don't necessarily need to get into fiber refs, but the useful thing here is that we can regionally control this behavior. So in this part of my application, maybe I want to enable batching, but maybe like somewhere deeper in my application, I want to shut it off for certain requests. You can even do it like on the request level in your layer. So you can, you know, basically pipe this to turn off request batching, right? So that granularity of when you can actually, how easily you can control requests that are batched and what's not, is extremely useful for all the points that Datner made as well. Okay, so I also want to touch on request caching. We might skip this exercise because it literally is doing this, but request caching is also an extremely useful thing to implement. There is a default cache that exists like when you run requests. I don't think caching is on by default. It is? Oh. It's not, right? It's false by default, right? Okay. Datner just sets it all at the top level. So besides batching, the other really useful thing about requests is because they implement equals, we can cache them as well. And you can control the cache that's used. So I for the life of me, can never remember the default capacity and time to live for the request cache that's like default in effect. But the request module has a make cache function, which you can see here. And we can pass in whatever capacity and time to live that we want. So we can, say we only want to cache 100 elements at a time. We only want them to be cached for a day or 100 milliseconds or whatever. And the cool thing about this is we can also do this regionally. So if you look at the get to do by ID example below, the with request cache and with request caching combinators allow us to regionally set the behavior of caching in our effect apps as well. So if I were to pass in, get Pokemon by ID, the same ID 100 times, it would run it the first time if I have caching on, and then the next 100 times it would immediately return because that request has already been fired off for that Pokemon ID. The point was brought up before, what if I have like some custom object that I'm passing along with my request and I want to enable caching? Then I would suggest using the data module from effect to make sure that your data types properly implement equals and hashing and that sort of thing. Yeah.
You're talking about like region here, like so. If I can enable caching for the specific resolver, can I provide the with request cache and provide the cache like at another point, like somewhere?
Sure.
It will share the same cache.
So imagine, so here's an example. I think I understand what you're asking. You can, if after I answer, if I didn't answer your question, just let me know. In this example, we have a specific cache that we're constructing for the get to do by ID like request itself, right? Higher up, so for this effect.request, literally just that request, it's going to use that cache and it's going to turn request caching on. For any other requests that we execute in our effect app, because caching is disabled by default, caching won't be on. Higher up in your effect application, if you have another request cache, that would be used for all the other requests. But then because regionally, we've said, okay, in this specific region of our program, we want this cache to be used, we can override the cache with one that we've like custom specified. So you can have as many caches as you want floating around in the program, as long as you've like basically said like, I want to use this cache here with the with request caching combinator. Does that make sense? And when I say region, maybe it's like an esoteric term. By region, I mean like a piece of effect code, like either a pipeline or a gen or whatever you're using. That particular region of your effect program would be affected by those combinators.
But I can have like one with request cache.
Yeah. Literally, you could pass it right before you run fork or run promise or whatever. Like you could say turn request caching on. I don't care. Use the default cache. I want everything to be cached. But yes.
But there is no way to control multiple caches at the level of your application. Like, so to say, like named cache. This region uses named cache A, this uses named cache B, and on the top of your application, you can say, this is my implementation for cache A, and this is my implementation for cache B.
I see. So you're saying that at the top level of your application, you would provide multiple caches, and then your requests would pick.
Yeah.
You could create a service in your effect app that contains multiple request caches associated to like the request IDs maybe, and then you'd still have to associate the cache manually with each request wherever you're using them. But you can't like say for this request use this cache at the top of your program necessarily, I don't think, right?
Yeah, if I was to do that, I'd use context, so and then create like a tag for each cache. Context tag for what cache you're using.
Right.
The named cache. You just then provide the cache to like the pickup provide. I'd probably use layers realistically, but then you could like associate a cache with the tag.
Yeah.
One or
I'm much noisier. I make the cache in the same layer where.
But yeah, it's very useful because all of these things can be done regionally, so you have really granular control over like requests that you're executing. And I think that request resolvers, batching, caching can all come together to allow you to build really nice, like if you use like the repository pattern, for example, in your app where you had like kind of like we did here where we had like a Pokemon repo, you can implement services that abstract over like the caches that you're using, whether you have batching enabled or whether you don't. And you can just expose like the interface that you want, but behind the scenes, when you're actually running those methods, you're batching these and you're caching these, and you have, you know, very granular control over like where you can turn these things on and off. So it's pretty cool, and used very heavily. For example, I think Tim, you use some of these features in Effect SQL or SQLFX, soon to be Effect SQL. Okay, sorry, there's a question.
Assessing when to use batching. So is it what? So one advantage is the deduplication, but why not just select an area of items and send one request?
So if to take a step back, the first question, like when you would use batching, the only decision point there is if your API supports it, you can use it. If it doesn't, you can't. That's like the first decision, right? Is like, do I have an API that even lets me batch if I have multiple requests coming in for something? And then the advantage of batching is sometimes you're not executing these requests in the same place all the time, right? Sometimes in your Effect app, you're running these requests all over the place. Batching allows you, regardless of where you're running these requests, as long as you've enabled batching for the region that you're running them in, Effect will batch all those requests together and then allow you to submit one API request instead of n API requests. So yes, you could manually aggregate the requests if you want. One sec. You can manually aggregate them if you want, but with batching on, you don't have to worry about it. And I'll let Datner.
Have multiple fibers, for example, that all feed into one result.
As long as you've enabled batching on the parent fiber that forked those children, yes. Because remember, batching is controlled by a fiber ref, which again, we didn't really talk about today, but it's a data type that allows you to propagate information across fiber boundaries like in very specific ways. So as long as you've specified in either directly in the fibers that you're running that you want that fiber batched, or in the parent fiber that forked all the fibers that are running requests that you want batching on, yes, Effect will handle batching them for you. So like if you have 10 fibers all running the same request that you've forked from some parent where you've enabled batching, all 10 of those fibers will have their requests batched.
But would you always use this type of batching resolver thing if you can?
I think it's very API specific. I would, because if I want to avoid, like most of the time you want to avoid sending multiple requests to an API if you can. But it's like very application specific, I think. Like I think you had a comment, Datner. Go ahead.
I think I understand what you're trying to ask. And the reason that you want to do this ritual to get the batching is that you get other things with that batching that includes the caching and then the duplication. And you can say, yeah, I can do all that locally, sure. But what if you want to do it in multiple ways? Classical example will be something like a graph request. If let's say you don't ask for 11 Pokemon, you ask for 10 trainers and their Pokemon. Suddenly we have different scopes that all request, let's say, the 6 Pokemon of each trainer. Yeah, you can batch those locally, but you can't batch all the 6 ones per each one.
It's a good point.
Either concurrency or not, that doesn't really matter in this specific case. You can still batch all of them together, and still, if some of them are duplicated, 2 of them have the same Pokemon, that one will be deduplicated. So like the maximum amount of Pokemon you can request is n, with n being like 10 times 6. But that's not the minimum or even actual.
So
Caching enable would mean that if you then later ask for 10 more trainers, if they ask for Pokemon you already got, those are also going to be omitted from all the batching you're going to do for the next round of requests.
yeah, exactly. And there's actually a really good example that Mike wrote in the docs when we first, because this whole batching, caching, request resolver business used to be a separate library in effect called Effect Query, which we ported from Zio. But then we found that the pattern was so common in Effect apps to be doing this type of thing that like in our own applications, we were almost always including Effect Query as a dependency. And we said, well, maybe we could integrate it directly with the Fiber runtime. So this is actually a feature we have in effect that Zio doesn't have in their library. They have to like install a separate library. But the reason I'm bringing this up is because after Mike figured out how to get this into the Fiber runtime, he wrote a really good set of docs, which I linked in the workshop channel, where he actually talks specifically about solving the N+1 problem that Datner was referring to here, with batching and caching and everything like that. And he also goes into a little bit about how this is even possible in like the runtime itself.
I have a question. So if I understand it correctly, if I have two fibers, one does some kind of computation and then gets the Pokemon from API. Other fiber gets the Pokemon right away, then does computation. Will in this case be the request cached?
So
Fiber 1, I'm doing the request right away. In Fiber 2, I'm doing some extensive computation that takes some time. Will like this request wait for the computation to finish and then cache it? Or how does if I'm like, if the caching aggregates multiple
yeah,
fibers that have caching enabled, how does it know when to actually make the requests?
that's
You know what I'm-
I do. So
And a sort of extension to that is, isn't there a risk that you run into deadlock, right? Because you're implicitly locking, you've got parent thread, parent fiber, next spawns 10 child fibers, and they're all then blocked, waiting on that parent request to go. And that's not really explicit, and you can get into the nest.
So if I'm understanding you correctly, the question is, you have some intensive work that's going on that eventually then results in firing off a request. And in another fiber, you also are submitting similar requests.
Submit it all like at the same time. There might be some like computation between, like it's not, if I have multiple fibers, I don't like it might not be the first thing that the fibers are doing to send a request. It might be some. So does the other, if I send a request, if one fiber sends a request right away, the other one sends it like after some thing.
It depends on your request resolver. If you're using a downloader from the experimental, then you can define time window, chronological dimension in which things should happen. But if you're using just the plain request resolver as is, it just looks around for how many things you can batch at the same time. I mean, that situation you're describing, it's out of that window because it's doing something while the rest of the resolver already finished. Okay, that's under request. And then you're asking, does it catch? The answer is yes. If once it arrives, the requests are no longer in transit and resolved, then it's gonna be cached.
So I think that the short answer to your question is yes, you could end up in a situation where you're blocking for a while if you're not necessarily, if I'm not sure I'm like 100% like understanding your question, so maybe we can talk like after the fact and then I can update you folks. I think that Datner's point about using a data loader in a situation where you might have like requests that you want to like control batching over a time window as well is like very helpful. But let's chat after the fact and then I'll update you folks with the answer to the question. So I'm not sure I'm understanding. I'm also not sure I know the answer to the question that you're asking. Okay. So let's go back to our presentation. All right, so we talked about request caching. We only have 1 more minute, so we're not going to do this coding exercise. The last thing I want to mention in the like 60 seconds I have left, I think, is, we also have a module in effect called cache, which is separate from request cache. The implementation is totally different, and the reasons that you would use it is different. Request cache is very specifically associated with like request itself. And the parameters that you pass in, you don't actually have the ability to do this like lookup parameter. But the cache module in effect is designed to help you cache expensive computations that you're doing in your effect app. So similar to the request cache, you can define a capacity and a time to live. But the really cool thing about the cache module in effect is that the lookup takes some key, again, as long as it implements equals. So if you've used like the data module, or if it's a primitive data type, as long as that key can be hashed with either, like it implements equals, it can be used as a key for this lookup function. And then the resulting effect will be computed, stored in the cache, and then every other time you run a cache.get to get the same thing, you'll immediately get the result that was cached before, until the item in the cache, till we've exceeded our cache capacity, or we've exceeded the time to live, and that like item in the cache is expired. So it's a potentially like very useful thing to use in your applications if you're doing a lot of intensive work that you want to cache. We're also considering, for the future, doesn't exist yet, but for the future, implementing something called like a cache backend, where we can like basically persist data automatically to things like Redis or Memcached or something like that, using like the cache module here. Doesn't exist yet, but it's like kind of like a potential thing that we've been thinking about. But in your effect app itself, if you have things that you want to cache and want to avoid running the same computation over and over again, you can use cache.make to create a cache. And that lookup function takes a key, which returns an effect. And every time you pass the same key in, it will either compute the value if it needs to, if it's not in the cache, or it'll immediately return the value from the cache if it was previously computed. With that, I think we are at time. Yeah.
Can I have a question about this? Can you actually like export it and save it to load in between?
Not yet. That's the cache backends is something we've been thinking about to enable things like persistence. Yeah. This is not. You can't really persist the cache at the moment, but it is something we've been thinking about because it could be potentially like a really useful thing to have. So yeah, I don't want to run late again, so I'll let you guys go for our 15-minute break, and then I will see you folks back here for our last session of the day. Okay. In this session, we're going to focus on observability and monitoring. And I actually want to touch on the topics we're going to cover before we go into the exercises, because I don't want to spend too much time working on the exercises without actually getting to talk about all of the specific topics that we're going to cover. So the presentation will be pretty quick, and then we can actually start doing some coding. The first thing I want to talk about in Effect is the logger interface. So Effect comes with a default logger. When you use the effect.log methods, it will by default use the default logger that we set up, which you've seen in some of the previous sessions, includes things like the log level, the fiber ID, the message that you're logging, etc. But the Effect can actually hold onto multiple loggers for your program. So behind the logger in Effect itself is actually a hash set of different loggers. By default, there's only one logger in that hash set, but you can add more. You can also remove the default logger, so you can really control how things are logged in your Effect application if you really want to get granular about it. And there's a bunch of combinators that allow you to do that, like addition of loggers and things like that into the Effect application itself. The logger interface allows you, accepts messages of type message and produces some output. So you can basically adjust this to your needs if you're implementing a custom logger. The interface itself is kind of cool because we get access to a lot of information that we can use to do our logging. We get access to the fiber ID that's actually performing that log operation. We get access to the log level, so whether it was info or trace or warning, whatever. We get access to the message, which is controlled by the generic. We get access to the cause if there is one. If the fiber had failed or something like that, we get access to the cause, the full cause. We also have access, we call it context here, probably a better name would be fiber refs, but we've talked a little bit about fiber ref as a data type. today. We haven't really gone too deep into it because it was a little bit outside the scope of today's workshop. But the fiber refs data type is, for like simplicity, you can think of it as a bag that holds on to all of the current fiber refs in our program. And we have access to these fiber refs, so we can extract things like the current log spans from the fiber ref in that fiber refs data type, or we could extract other information from pre-existing fiber refs, like really whatever we want that's stored in a fiber ref, we can gain access to in our logging. We also get a list of the log spans that were passed to this log call. We also get the annotations that were passed to that log, and we get should probably be called timestamp, but we get a date passed in that we can use to format the date however we want. We are going to have some exercises in a little bit where we'll implement some custom loggers. The first one will be implementing a batched logger, which was a question we got on Discord a while back. Basically collecting all logs within some interval and then outputting them all at once. Just an interesting use case for a logger. And then we'll do another one if we have time, where we're going to use a logger to actually update a metric that basically indicates how many times we've actually called different effect.log combinators. But we'll come back to this in a moment. I wanted to briefly touch on the metrics that we have available to us in Effect. We have access to 5 different metric types in Effect. And metric represents a data type. It's a concurrent metric which accepts some input and aggregates that input to some stateful value of type out. The type parameter here controls the metric type itself. And what I mean by that is we have 5 different types. So the type would be either a counter, a gauge, a histogram, a summary, or a frequency. And these metric APIs the metric APIs that we have in Effect are extremely powerful. They allow us to track pretty much every aspect of our Effect program execution if we want to. We can track things like successes in our Effect program. We can track failures. We can track how long things take to execute. And we can roll that all up into different metric exporters that we are always working on implementing. I'm not going to talk about the individual metrics just yet. I want to at least cover all of the pieces of observability that Effect provides before we start like the exercises and whatnot. So besides logging and metrics, we also have built-in support for instrumenting your application with traces. It's extremely easy in Effect to trace a particular region or add information to the spans that you're exporting. So in this example, I'm logging some information, I'm implementing some delay, then I'm annotating whatever the current span in that region is. I'm annotating with some additional information. Here I'm just using key value, but the point being is like you can gain access to the current span and annotate it with different pieces of information. And then the effect.withSpan combinator wraps a full effect and allows you to annotate it with a span. You can also pass additional arguments to withSpan, like attributes that you want to annotate directly on the span. But all of these things come together very nicely when you start exporting these traces into observability tools. So I do want to point out also that logs inside a span will show up as events in your traces. And what I mean by that, I know this is extremely small, it's not designed to be read. But the point here is when you execute an Effect program that has tracing enabled and you export those traces to some visualization tool, you can get a really nice waterfall diagram of all of the spans in your Effect application, how long they took to execute, the information that you've annotated them with. And if we look, this is very small. If we look at some of the information that we have access to, at the top here, these are the span attributes that we've attached. These are resource attributes that were attached globally to the resource itself. And then you can see at the bottom, well, it's very small, but at the bottom here, these are events that occurred within that span. And so any logs that occur within that span would be exported as events into the trace as well. So you get there's a ton of built-in observability tools that you can use to instrument your effect application. Between logging, metrics, and the tracing APIs, you can pretty much get full observability into your effect programs. So let me just see if there was anything else. So with that, I know we went over these things a little bit quickly, but maybe let's start with a coding exercise where we work with a custom logger. So in session 4, under your exercises, exercise 0 has you folks creating a custom logger, which batches logs and emits them as a collection of logs over some fixed window. So we basically get a window as our argument. I don't know why I made this an object. And the goal here would be to basically aggregate these logs over some like window and emit them. So your job here is to try to implement the aggregation functionality for this logger. And you guys can go ahead and remove this piece of code. The other thing I want to point out to you before we get started is I'm using a effect combinator called locally scoped with here. There are several combinators in the effect core library, in the effect data type, that allow you to manipulate fiber refs directly. The fiber ref, in effect, that stores the current set of loggers in your program is on the fiber ref data type called current loggers. And you can basically control what is currently added to these loggers within a particular scope. So inside this, this call to effect.locally scoped with, what I'm basically saying is that we're going to create a scope. We're going to add the logger that we're implementing to our set of loggers within that scope. And then when that scope is closed, the logger automatically gets removed from that fiber ref, that hash set in that fiber ref, if this makes sense. There are several other combinators for working with fiber refs here, but because we didn't cover them today, I implemented this part for you folks. I just wanted to at least point it out so you know what's happening here in terms of like how we're actually adding a logger to our program in this example. But the goal here would be that we get batches of logs over some window. So every 2 seconds, we'd emit some like batch of logs in this case. So why don't you folks get started, and I'll circle around and help because I know this one might be a little challenging. So just in the interest of time, we'll go over the solution really. I think there was a lot of yeah. Darn it. Thank you, Tim. Thank you for letting us know. I think there was a lot of really good discussion that came out of this exercise, so I'm really glad. I saw a lot of people reaching for an effect runtime using queues to like kind of create the buffer. I think that's like completely valid as well in terms of implementations. I went with a much simpler implementation here where because effect.gen is internally wrapped with suspend, we can allocate mutable state safely inside gen. So I just created a log buffer array. I created a reset buffer effect that just resets the buffer. And then I created an output buffer effect that console.log joins the buffer together and then resets it. I think some of the interesting pieces to highlight here, so specifically with the logger, I chose to grab the string logger that's exported from the logger module, which I believe is the one that we have that formats logs nicely. We can actually test it. TSX version 4. So string logger in this case is the one that we have by default that formats things nicely as a string. So I grabbed that logger and mapped the message and pushed it basically into my log buffer. And then in terms of implementing the scheduling, the window, I think a lot of people ended up arriving in to a similar solution as this. So I think that's great. I created a schedule. This was the way I chose to do it. I created a fixed schedule with our window and composed it with a schedule that repeats forever. So we end up with a schedule that operates on our window and just keeps going. You could also have used effect.forever. I think that's valid. But basically here, I use our output buffer to output the buffer, running on a particular schedule. I used a combinator and effect called ensuring, which if you look, do we have documentation? It's basically a way to make sure that the finalizer that you pass inside ensuring is executed if the effect that's running, if the effect that's passed to it is successful, fails, or interrupted. It's kind of like a finally block. Just making sure we clean up the output buffer. And then two things I want to highlight here. I think I talked to some folks about this, but what we're essentially doing here is forking a background fiber. The first thing I'll highlight about the background fiber that we're forking is because we already create a scope here with our locally scoped with. I mean, even if we didn't create a scope, using fork scoped in a background fiber like this is sometimes, especially if we're attaching it, if we're creating our background fiber inside a layer, is often like good practice, just so that when you basically have control over when that fiber shuts down. The scope that you pass to the effect that's running this background fiber, when that scope is closed, that fiber will be shut down. So it's kind of like using fork and fork scoped for this example are somewhat equivalent, but fork scoped often is what I tend towards, especially because it gives you that granular control. And then the other piece that I wanted to mention here is whenever you fork a background fiber like this, you have to be really careful about where this effect actually gets executed, because if this gets, if I didn't have this interruptible piece here, if this effect got executed in an uninterruptible region, for example, like in the acquire piece of an effect acquire release, or in any other region that maybe we've marked as uninterruptible for some reason, the fiber won't be able to be interrupted because it inherits interruptibility from the parent. So in order to make sure that our fiber can shut down, the child fiber can shut down if it's interrupted, we can explicitly mark that region as interruptible. So that basically makes sure that this region has interruptibility enabled, so the fiber can be shut down properly. I think there were multiple valid ways that people did this, by the way. Like I said, I saw a lot of people reaching for like runtime, pushing to the queue, pushing to a queue, trying to grab from that queue. I think that's also like a pretty valid way to do this. But anyways, hopefully a somewhat useful exercise for just getting a feel for how we could create a custom logger. There is another exercise that I have for creating a custom logger, but we're gonna not do that right now. What I actually want to do is quickly demo the effect app that Tim and I built for this workshop specifically. It's a CLI application, and you guys all have access to this as well. And if you want, I can drop an API key for OpenAI into the advanced Discord channel that you guys can use at least till the end of the workshop. Yes, I'm trusting you all with incredible power. No. This example app that we built is a CLI which basically allows you to train a model on markdown files and then execute prompts against the model that you just trained. So if we export this API key, and we also make sure that I've started our compose stack. So, oops. the other thing that this repository includes is a mock like tracing setup or observability setup with Tempo, Prometheus, and Grafana. So all of your traces, metrics, everything like that that you run in this app would be exported locally to the Compose stack that we've set up. Okay, and then if I remove the previous time I did this, basically this will probably not work on your local machines as well. It would probably be best if you ran this in Gitpod because there are some native dependencies that we use for an SQLite extension to store the embeddings in a vector format, and they don't play nice with many systems. So I ended up using Nix to ensure that we all had the same version, at least or the same version of SQLite BSS, at least in Gitpod. So if you use Gitpod, it should work. So let's see. So if we run pm tsx source bin, and we train it, there are two commands in this CLI. I'll make this bigger. There are two commands in this CLI. We have train, and we also have prompt. Train allows you to pass in a markdown file and a path to a SQLite database that'll be created for you. And it will use OpenAI to train a model, to generate embeddings for that markdown document. The CLI application also does chunking of the document and a whole bunch of other things that we can look through if we have the time. But a lot of the things that we discussed today or didn't necessarily get a chance to discuss, for example, the rate limiter that we were going to implement, the data loader, and a bunch of other patterns are present in this CLI. So you can kind of use it as a reference for maybe like an advanced real-world effect application. Tim and I tried to put as many of the patterns that we discussed today in here. But if we train this on, I think there's a fixtures I included with an effect file. So you'll see we get a bunch of logs basically saying that we're chunking up the document, we're sending it to OpenAI, whatever. And ports. If we visit our Grafana implementation, we can, using Tempo. Say it again? Oh yeah, I will zoom in. So using Tempo, no, I can't scroll. Fantastic. Using Tempo, we can grab our service, run a query to get the most recent trace ID that we exported. So I had run this before, which is why there's another trace ID in here. But if we take a look, so the CLI has tracing set up as well. So we export a bunch of different information. There's no metrics in there right now, which if you guys want to play with that, you're more than welcome to. But if we take a look specifically at this trace, I wish, there we go. Is there a way I can make this full screen? Anybody know? Wow, that did not work. F2. All right, let me zoom out a tiny bit. So I'll zoom out a tiny bit, but you can see, hopefully, somewhat, the waterfall that was created for this particular invocation. Now, obviously, if you had like a long-running effect app, you'd be getting different, you'd have a like separate different kind of waterfall here, but this waterfall represents the invocation that we just ran for training our OpenAI, or getting our OpenAI embeddings by training it on that effect document. And you can, if we take a look, you can see the hierarchy of spans that we get. So spans are regional as well, right? So as we attach spans to our effects, we get a hierarchy. So we can basically trace the execution of our effect program. For example, if we look at, we start with chunking the document. We attempt to upsert, we grab the embeddings, we batch them, and then we set the embeddings in this upsert method. And somewhere in here, we can take a look and see like what attributes we had on that particular span. So this basically gives you pretty granular information about what actually just happened when you ran your application. And like I mentioned before, in addition to span attributes, which you can attach to spans either at the time you call with span or with using different combinators, your logs that you execute within a traced region get exported as events. So you can see things like the log message and any other pieces of information that you annotated those logs with, right? So not only do we have the ability to add attributes to our traces, we also have the ability to annotate logs, right? And any of the log annotations that you have will also be propagated to this event. So pretty useful. And Anna was also kind enough to create a dashboard for us as well, which utilizes the some of the default metrics that we get from Prometheus about our execution to get some information like, you know, the duration of all the spans we have. There's a P99 in here as well, but we would need to run this a few more times to have that be somewhat accurate. But you kind of get the idea here that with logging, tracing, and we didn't specifically annotate any metrics in this effect app, but you get a lot of power and introspectability into your effect programs. And this local setup should really work for your apps as well. I can show you really quick. Whoa. Is it still readable if I go down one more? Somewhat readable. So in our CLI, we have a whole bunch of things that we're importing from OpenTelemetry, but we also have the effect OpenTelemetry package, which exports this, which has a Node SDK module. And this is also documented in our docs, but the Node SDK allows us to create a resource which we can attach span processors and metric readers to. So in this case, like I'm using a batch span processor that uses an OTLP trace exporter to go to Tempo and has a Prometheus exporter for the metrics. But you can kind of get an idea how you can start really introducing trace, like just with this and the Docker Compose setup, you have tracing in your effect app. So you guys are free to use like the stuff from this application. It's all open source. But yeah, I encourage you folks to play with the tracing setup. The other thing we can do really quickly is run the pnpm tsx prompt, give it the embeddings we just generated, and we can maybe say everybody's favorite question. What is effect, right? And if you remember all the way to the beginning of this workshop, we talked about wrapping external APIs and how you can go about doing that. There's like the one-off method, this flexible method, and then like kind of the all-in on effect method. Well, the two OpenAI examples that I showed you of wrapping like the chat completions and messages API messages are both in here and being used in this like production grade Effect CLI application. So if we look at the OpenAI service, again, many of the things that you'll find in here are things that we discussed during the workshop. So we're basically wrapping to get these completions, the OpenAI chat completions API, and then unwrapping that into a stream so that we get the streaming output in our CLI like we saw. So please explore this CLI application. I am required to invalidate the API key after the workshop, I was told. So if you didn't get a chance to use it, I'm sorry. But I hope that you all enjoyed this workshop. I really hope that you folks got something out of it. I really appreciate everybody's attention. It's not easy to pay attention for the full day in a workshop format like this, so I really hope that we were able to keep you engaged. And again, we need feedback. We really this is the first time we're running these workshops. We really want to know if this format was useful, if you guys would like to see other things, if doing things a slightly different way would be more beneficial. So please provide your feedback, whether it's directly in Discord or in the feedback box, whatever you're most comfortable with. Really, thank you all very much. It was a lot of fun for me to do this. So, what? Yeah, so thank you guys very much again. It was a lot of fun for me to do this. Yeah, I really hope you all enjoyed it. So thank you.